This is a screencast for NAT 1780. In the screencast, what I want to do is talk about H2O and the different states that it can assume in Earth's atmosphere, and also to then generalize that into kind of an entree into a discussion of what's called a phase diagram for the system H2O. So one of the curious things about H2O is that it can naturally exist in each of its three possible states in Earth's atmosphere. So we could find H2O in the solid state, and actually that's jumping to where I want to go, so we'll start back here. We could find H2O in its solid state, which is of course ice, and so again here is an artist's rendition of what ice might actually look like. Maybe not quite an artist's rendition. So that's the H2O in its solid phase. And what we want to do is also, of course, indicate that H2O can exist in a liquid phase. Actually, let's draw that in a slightly different color, maybe to draw a little bit of an emphasis to it. Not much better a sketch, but I think you get the idea. And then, of course, finally, H2O can also exist in the gas or vapor phase, which I'm attempting to draw here. So here is, of course, we call the liquid phase water, and the vapor phase water vapor, with a U because we honor the Canadian spelling. So again, just to kind of reiterate, that means that we have H2O in its solid phase, in its liquid phase, as well as in its gas phase. And of course, through these processes that we will start to become familiar with and refer to as phase transformations, we can actually transfer states. So for example, what we can actually do is take some H2O. Let's start off in the ice phase, and we can transform that into the liquid phase. Whoops, that got a little away from me there. So let me just go ahead and just clean that up a little bit. Alright, let's get back to this. So trying to look at the transformation from ice, the solid phase, into the liquid phase, and of course that transformation is something that we refer to as melting, and that's something that can be achieved very easily. Something you're also, I'm sure, very familiar with. And of course then we can also take the H2O that's in the liquid phase, and we can evaporate it to produce the gas equivalent. We can also go backwards. That's one of the really interesting things about phase changes. So phase changes are reversible, so we can actually go from the vapor state back to the liquid state through the process of condensation, something that we'll end up speaking a lot about in NAT 1780. And we can also, of course, go from the liquid phase back into the solid phase through the process of freezing. Now, there are actually some additional phase transformations that are also possible, and these ones are, of course, a little bit less familiar. It is possible to go all the way from the solid phase to the gas phase. Not easily, apparently, the way I'm drawing. So let me just clean that up, and we'll try that again and try and get over to the to the gas phase with a little bit more dexterity. Obviously, I'm still getting myself accustomed to this this technology, as you can see. I amuse myself. Okay, so here we go. Let's try and continue that on to the gas phase here. The phase change transition that takes us from the solid phase directly to the gas phase, bypassing the liquid phase, is something called sublimation. And as I say, that's probably something that might be a little bit less familiar to you. And of course, we can actually go backwards as well. We can go from the gas phase back to the solid phase, and that's through a phase change process called deposition. Okay, so those are all of the those are all of the potential phase transitions in the system H2O. Okay, now at least in terms of changes of state from between solid, liquid, and gas. There are some other finer points that we can place upon this, the subtle distinction between phases versus states. That's something that we'll talk about later. The other thing that I just want to remind you of is that any phase change that takes place basically going from left to right, let's put that in blue just to emphasize this. So phase transitions that proceed in this direction, so any of the three, melting, evaporation, or sublimation, all of those require energy. And so those are so-called endothermic. Wow, that's some really bad spelling you've got going there, Ian, so we better fix that up. Let's see, endotherm. Let's just try and clean this up a little bit. Endothermic. Again, now you know I don't write on the board in class. So these are all so-called endothermic phase changes or changes of state. In other words, they require energy to be input in order for them to happen. And of course, going the other way, and actually maybe I'll put this in red just to emphasize the opposite. When you go in the opposite sense, from right to left, these are all phase changes that actually release energy. So we refer to these as exothermic phase changes. They actually release energy. So condensation, freezing, deposition, the energy that was required to drive the transitions the other direction is released. And so these are so-called exothermic phase changes, moving from right to left. Now, if you were to further add some additional detail to this, let's just insert a new page here, a nice new blank page. Suppose we start off. Let's draw ourselves a temperature axis here. So this is supposed to be temperature, and just for familiarity, we'll do this in degrees Celsius. And let's also add on some critical temperatures. How about 0 degrees Celsius and 100 degrees Celsius? Well, we know that some pretty special things happen right around these two particular critical points. In fact, it's the physical properties of H2O that are responsible for defining these critical points in terms of the Celsius temperature scale. So what happens at 0 degrees Celsius if you take H2O in the solid phase and you start to heat it up? Of course, it starts to melt right at 0 degrees Celsius. If you take, if you take H2O that's in the liquid phase and you raise the temperature of the H2O that's in the liquid phase in some kind of a container, a kettle for example, you know that it starts to boil at 100 Celsius and it produces vapor. So in fact, these transitional points turn out to be rather critical. We identify, in fact, 0 degrees Celsius as the melting point or the freezing point equivalently for H2O, and we would speak about the 100 degrees Celsius as being the boiling point for H2O as well. So these turn out to be rather critical values for temperature in this particular system of H2O. Maybe I'll also just quickly put that up here as well, that we're talking about phase and phase changes, transitions of state in the system H2O. So another way of looking at this is, of course, that basically for temperatures below 0 degrees Celsius, this area that I'm trying somewhat effectively, emphasis on the somewhat, to shade in here, what we see, of course, is that we have H2O existing in the solid phase. We have melting that happens around 0 degrees Celsius. H2O exists in the liquid phase in this internal region, and then it's, of course, in the gas phase over here. Let's just quickly rewrite that up here just to make this nice and clear. Now, the other point that we actually haven't really paid any attention to here is the fact that these changes in state, changes in phase, they also are affected not only by temperature, which is the single variable that we're showing here on the horizontal axis, they're also affected by pressure. And in fact, what we haven't actually said here is the fact that, let me just rewrite that for consistency. What we haven't actually indicated here is the fact that for a diagram like this that we're showing you here, pressure must be held constant. In other words, it's the kind of experiment that you could carry out at home, for example. But of course, we can vary pressure, and when we do, what we find out is that we get a much more complex looking diagram, if you like, that plots out the entire sort of zones of in which you can have a solid, liquid, or gas phase of H2O. And that's actually what this diagram on the next page slide is attempting to show you. So this is from the lecture notes, and what you can see here is that we have pressure on the vertical axis, and we have temperature on the horizontal axis. Now notice that the units of temperature are a little bit different here, and I'm just going to quickly make a little notation about that. So in fact, for the case of temperature, what is often done, just for now we'll just say it's for the purpose of convenience, is we end up using a different scale for temperature measurements. That this is often used by physical scientists, including chemists and others, and of course ourselves. So we actually represent the temperature in a unit called Kelvin. It's named after a famous physicist, chemist, physical scientist. You take the temperature in degrees Celsius and you add 273.15 to that. So 0 degrees Celsius basically ends up corresponding to this funny looking number here, 273.2, when we round it off to 1 decimal place. So it's just a different scale for temperature, and as I say, what you'll often find this being used, and there are some reasons for that that we'll talk about at a different time in the course. This is also a little bit of an old diagram, so the other change I'm going to make here is I'm just going to highlight the fact that pressure, which is measured on the vertical axis here, is given in these funny looking units called atmospheres, and of course that's not anything close to what we use today. So in fact we use a different unit today. In Canada, we use units called hectopascals. So, in fact, 1 atmosphere, you can see why it's a convenient unit. 1 atmosphere is equal to 1013.25 hectopascals. Okay, in the U.S., you'll notice that they still make use of millibars, and it turns out that a hectopascal is exactly equal to a millibar. So you may find 1013.25 millibars more familiar to you. That is in fact the value, the so-called standard value of atmospheric pressure at sea level. 1013.25 hectopascals or 1013.25 millibars. And again, later in the course we'll actually talk about why that is in fact the case. So the diagram that we produced on the previous slide, this one here, which had only a scale for temperature, as you can see in the horizontal here. So this is our single scale here, just a scale for temperature. There was no pressure variation whatsoever indicated. That value corresponds to basically, as I was saying, the kind of thing that you would get if you did this experiment by yourself at home. And it basically corresponds to this horizontal line in this this phase diagram. So actually we call, I'll write that up in a second. So this this horizontal line here, which is almost horizontal and it's almost straight. But basically this is the line that we had in the previous diagram. So in fact what we were looking at is just a single line. We were looking at just variations in pressure at constant temperature. I beg your pardon, other way around. We were looking at just variations in temperature with constant pressure. The pressure was held constant at 1 atmosphere, or 1013.25 hectopascals, and we produced the variations that you saw. And what we ended up finding out was that we melted solid H2O in the solid phase into the liquid phase at this value here, and if you follow this drop down here, you can see nicely that that corresponds to basically right around 0 degrees Celsius. We can talk about why there are some subtle differences here. And then over here, what you can see is the second transition that we talked about, the so-called boiling point transition, where we move from the liquid phase to the gas phase, and that occurs, as you can see here, at 373 Kelvin, which corresponds to essentially 100 Celsius when you take off the conversion factor that I was talking about down here. Okay, let me get rid of some of these little distractions here, and then we'll wrap things up. So basically what I was saying before is that we're now looking at what we call the phase diagram. Actually, maybe that's fine. Phase diagram for the system H2O. And what you can see here is that this phase diagram, it illustrates that when you look at the potential states or phases that H2O can assume, that of a solid, a liquid, or a gas, you end up with this two-dimensional nature to what actually is possible here. And sorry, as I say, I'm still getting used to the tool. Okay, anyway, we have a phase diagram for H2O. You can see that by varying both temperature and pressure, we end up with this two-dimensional area of possibilities, and basically that allows us to map out the entire range of potential states for H2O. Now, what this also means is that we could, for example, ask the question, for a given value of pressure and for a given value of temperature, which phase would we expect H2O to be in? So we can actually ask questions like that as well. So for example, we could look at a value, atmospheric pressure has its maximum at the surface. So in fact, as you move away from the surface of the planet, you'd actually be looking towards lower values of atmospheric pressure. So maybe somewhere around here. And it's kind of a funny looking scale, as you can see here, because of the nature of the variations. They're quite rapid. But maybe somewhere around here you would have about half an atmosphere or something like that. And you can see that if you follow this through, for example, you would end up at a value here, maybe about halfway between 273 and 373 Kelvin. You'd end up with a value for H2O in the liquid phase. So you can actually use a diagram like this to give you information about the phase or the state that H2O is in as well. So phase diagrams are extremely valuable. What this is just a very brief introduction. What I tried to do here, again, just to quickly review, was I started off by discussing the various phases that H2O can assume. You can see that H2O can assume a solid, liquid, or gas phase. There are precisely 6 ways in which transformations between those phases can take place. We've labeled them. Some of the transformations require energy to be accomplished. They're shown on the upper half. So melting, evaporation, and sublimation all require energy. That means that they're endothermic phase transformations, whereas the ones in the lower half of the diagram, condensation, deposition, freezing, all release energy, and they are therefore known as exothermic phase changes. Phase changes do not involve any change of a chemical nature. There are no chemical reactions taking place here. It's H2O in every case, and as you'll see from other components of the course when we talk about H2O, this has a lot to do with the nature of bonding between individual molecules of H2O. We then looked at a constant pressure scenario. We kind of pretended we didn't even know that pressure was a variable that had any relevance here, and we just varied the temperature in a systematic fashion from somewhere below 0 degrees Celsius up to somewhere above 100 degrees Celsius, and we're able to produce various transitions. A transition from solid to liquid, if you like, when we melted ice and produced water, and we were able to boil and produce water vapor when we took water and brought it around to 100 degrees Celsius and then above. And then, of course, theoretically, we can actually go back as well. So another important characteristic about phase changes, and maybe I'll just write it over here somewhere where I can squeeze it in, is that phase changes are actually what are called, they're a good example of reversible processes. Okay, which means that you kind of, it's like having an undo operation. So for example, if you took ice and you melted it and produced water, the undo operation would be to take the water that you produced and freeze it back, and you'd have ice again. So you can actually go from a starting point to an intermediate point back to the same starting point. So that's an example of a reversible process. And we're actually going to, of course, it's actually a collection of a couple of processes, but what you can see, what you'll find out in the course is that we'll actually uncover a couple of examples of this. Okay. Oh, and then just to summarize the last slide here, where we actually have the phase diagram itself. So this is a properly produced phase diagram for the system H2O, and what you can see is that when we allow both pressure and temperature to be variable, we end up with this two-dimensional set of possibilities for the different phases and the relations between those different phases as defined through this phase diagram. And because both pressure and temperature vary in Earth's atmosphere, this is in fact the framework that allows H2O to assume any one of its three primary states. So we'll be talking a lot more about this in other components of the course, and I would say that's more than enough for this particular screencast, so we'll end it right now.